Okay, so our second speaker of the afternoon is Ignatios Antoniadis, and he's going to tell us about the Swampland program, experiments and supersymmetry gravity.
We're going to start again the thinking program and the getting of the case so my motivation would be we start with the problem of scales that if given scale it appears in other physics. The theory of string theory that aims to describe nature. And these are three of the scales that will be relevant to my talk. So we are here in the accelerators. Oh, it's off. So I can put it. So the accelerator, the LHC, let's say, probes the electroweak scale. We have somewhere here the scale of quantum gravity, and that's the scale of the dark energy in milli-electron volts. And would like to discuss two scales that we don't know where they are, but they are probably there. One is the scale of new physics, which is possibly related, at least I will talk about supersymmetry, which can be anywhere here. It's an essential ingredient in string theory. And another scale is inflation, which again, we don't know if it's like supersymmetry, if it is there, but it can describe, it describes, it gives a good description of cosmology. Yeah. The string theory is a candidate of fundamental theory. It has two ingredients that I would use. The first is the existence of extra dimensions. And the string coupling can also be treated as an extra dimension in M theory. The possibility that these extra dimensions have are associated to compactification scale, which are much different than quantum gravity scale, is due to the fact that to the existence of branes. So if matter and gauge interactions are localized in branes, then the transverse dimensions can be large, and therefore the string scale can be a parameter. And this opens the possibility to address many, in particular, problems of scales in a new way by, for instance, varying the string scale, which would be related to the scale of the species scale that we had this morning. So it can be everywhere in this. Sorry, I must be familiarized with this thing. So anywhere here. Of course, the size of extra dimensions will be fixed are fixed by the moduli stabilization, or which are in terms of the discrete fluxes, and this gives rise to a huge landscape of icon. And this is where the Swampland program comes to my view. That it provides an input of or a guidance principle to look in the landscape of icon. For instance, we know that that not all effective field theories can be consistent with gravity. The anomaly cancellation is not sufficient. But there are additional conditions that could bring constraints. We had many. Usually, these conditions are conjectures because it cannot be really proved or partly are proved. They're mostly supported by arguments based on our experience on string theory and on black hole physics. In my talk, I will discuss mainly the distance duality conjecture, that at large distance in the field space, there is a tower of exponentially large states with masses which decrease exponentially with the distance. So phi is a canonical normalized field correspond to the distance in the field space. The second part of the duality, the second part of the conjecture says that this tower of space provides a weakly coupled description of the low energy theory, which breaks down at a scale which is the species scale, which we have this morning, so we will not discuss more. And this tower can be either a Kaluza-Klein tower, corresponding to the decompactification of some extra dimensions of size r, in which case the distance is the logarithm of the radius, or it corresponds to a tower of string excitations, where the associated scale is the string scale, and the distance is the logarithm of the string coupling, and that's the emergent string conjecture. So the main physical question is whether the smallness of some physical parameters compared to quantum gravity scale could be a signal and an indication that we live, I mean, the physical theory that describes natural for these parameters at a large distance corner in the landscape. And one early example was at the time of four-dimensional theories, string theories, where this paper had shown, had observed that for Gaussian compactifications, which were at that time developed, that the existence of a light Gravitino or Gravitino, in other words, of a spin 3/2 particle in the spectrum, lighter compared to the string scale. There is a tower of states with the same quantum numbers, and masses will grow linearly above the lowest Gravitino mass, which signals a decompactification. So this n in Gaussian models was an integer, which we could bound within this model. So for full fermionic constructions, this n was less than 10, while for constructions of compactifications based on bosonic lattices, the n was up to 1,000, of the order of 1,000. So this relation can be recast in this way, that there is a compactification scale, which is in this case proportional to the Gravitino mass at the large distance limit, with a parameter here, coefficient, which is not too large or small. So now I come to the proposal of dark dimension that was proposed by the group of Kumru, saying that precisely that the cosmological constant could be the smallness of the cosmological constant could be related to this, that we are in it's a signal of the large distance limit with the power here A. It's not necessarily linear. which is bounded in this region. So these are three important ingredients. The first is that the distance in this case is the logarithm of the cosmological constant. And this was argued based on the Adida-Sitter distance conjecture that we had this morning by Dieter. And then this coefficient, the upper bound comes, it's a unitarity bound due to Higuchi, comes from the fact that the massive spin two particles, so the lowest Klein extension of the graviton, should have a mass which is bigger than h squared, where h is the Hubble constant, the inverse Hubble radius, which is proportional to lambda. And the lower bound comes from an estimate of one loop correction, unless if there are cancellations, of course, which should be 1 over, which goes like 1 over m, 1 over r to the 4, m to the 4. Putting now the observations, the constraints on the observations here. I mean, this is a big hierarchy, 10 to the minus 120. On the other hand, the mass m associated to the dark radius should be bigger than 30 microns from the Newton's law experiments, from the validity of the Newton law. And this pushes the coefficient A to be very near to 1/4. So the proposal is that this coefficient is actually 1/4. And then the astrophysical constraints that do not allow more extra dimensions. So only one is allowed. Astrophysical constraints essentially from the supernova. But constraints if extra dimensions appear apart from this, there should be larger than about the inverse 10 MeV, which is the temperature of the supernova. And then this fixes the species scale to be of the order of 10 to the 8 ZeV times this parameter lambda, which is constrained in this region. The upper bound comes again from the Newton's law, and the lower bound essentially comes from, it's a heuristic argument on the power of A. If it is too small, then the power changes. And obviously, in this case, the tower cannot be a string tower from observations. So this was a nice proposal. And there are it comes with other interesting physics applications. One is the neutrino masses that are we know that are of the same scale. Actually, for different reasons, people study the possibility that I mean, this was already an old idea that there is a possibility that the neutrino, the right-hand neutrino, is a bulk state, and therefore the oscillations could explain the hierarchy of the neutrino masses. These analyses were done repeated recently using the new data from neutrino oscillations, and give a bound for 3 neutrinos in the bulk of dark radius less than 0.4 microns, which means that the coefficient, the parameter lambda that I discussed before, should be rather small, 10 to the minus 3, and the scale goes up to 10 to the 9 ZeV. Another consequence is the possibility which would be either molecular 5 dimensional by multiple quants. The reason for 5 dimensional is control the rate and the rates smaller than the range and extend this extend the reason for the markets in order for primordial approach to explain current percentage of market. Alternatively, dark matter would be also counted by consequent excitations of the galaxies. By real with decreasing mass due to internal decay. It's a nice idea that realizes the proposal of dynamical dark matter, in which the numbers, the dark matter mass peaks around MeV at the time of matter radiation to quantum, and it goes up to the day. There is also some arguments that possibly there is some possibility of proposals. So now I'd like to, so up to now, it was for review. Now I would like to discuss two issues. The first is related to the how this scenario could be put in cosmology, how could be related, for instance, to inflation. The inflation scale in general is written by this formula, because it's the Einstein equation. Where I start here is the normal Planck mass. However, in the presence of many degrees of freedom, like in the case of vector dimensions, then this scale Planck mass will be replaced by the effective strength of duality, which takes into account all the line degrees of freedom, number of species, up to the inflation scale. So, on the other hand, we know this is important because in sometimes there are claims, not sometimes, I claim that if primordial tensor fluctuations are measured, then this will fix the scale of inflation. This is true under the assumption that gravity interacts in the same way now as at the inflation scale. And it's not the case if there are many degrees of freedom, like the planning state. So, in other words, observational parameters, cosmology are dimensionless, and therefore all predictions are made in terms of the quantum duality scale, but this quantum duality scale is the speed scale at the time of inflation. So that's a relation, for instance, between the carbon constant at the time of inflation, scale, and the tension scale. Now, putting the numbers and the dimension and the propagation scale of electron volts, one finds that the effective scale of duality is 10 to the 9 dB, and therefore the inflation scale is less than approximately 10 to the 7 dB taken into account as less than 0.05. However, there is an extra bound, more stronger than this, which comes from the difficulty bound that I mentioned before. And so if one assumes that at the time of inflation, the extra dimension was fixed at the micro scale, then the difficulty bound implies that the Hubble parameter should be less than electron volt, and therefore the inflation scale should be less than 100 dB, much less than 100 dB. Now, this is still possible in principle, but another interesting possibility is that the extra dimension expands with time at the same time with the universe. So it was a question how many equals you need to bring the extra dimension from the Gravitino scale length to the minus length. You find 42 equals. And this is already within the region where one needs in order to solve the horizon problem, then with the concentration scale. However, okay, more precisely, we are attempting to relate the five-dimensional metric to the four-dimensional metric by normalizing the Planck scale, the four-dimensional Planck scale. In use of the four-dimensional Planck scale, there is an extra scale into here, the four-dimensional metric, which means that if the extra dimension is inflated by a certain number of inputs n, then space-time is inflated more by 3 half times the same number of inputs. So we're at around which is likely the number that one needs to produce also the right. So that is this proposal. Of course, we have to say when the inflation ends. For this one, or to replace the inflation by the four-dimensional inflation by producing the five-dimensional field, the new five-dimensional inflation. This will have a potential. Stop the inflation. After the stop inflation, we can populate the four-dimensional universe with the standard model boundary. So the easiest way to do it is by assuming that the inflaton has a coupling to the brain, such that you have a coupling like I can used to neutrino massive. This coupling will be suppressed by the volume of the bar, the same from the wave function normalization, like the light in Gravitino. So I can compare the decay of the inflaton to standard model particles, and require that this decay is higher than the decay to the consequent exertions of the gravity, which occurs in 5 dimensions, and one finds that the mass of the is less than 1 keV. So this is an interesting idea to explore further. Now I'd like to move on to the other scale, which is the supersymmetry breaking scale, for which I mentioned at the beginning. There is a Gravitino mass conjecture, which has been formulated more recently in the context of the program, which replaces the theorem dependence that I mentioned before the quotient models by a power of the Gravitino mass M in some system in Planck units, where the process is bigger than 0. Now, this relation for the Gravitino mass to understand that Gravitino mass is not directly related to the soft terms of supersymmetry breaking standard model. But the case we will take 2 steps. The first is the Gravitino mass is related directly to the scale, to the order parameters of supersymmetry breaking, the expectation value of F term or P term at the sector that breaks supersymmetry. So you have this relation of the Gravitino mass proportional to the supersymmetry breaking square in Planck units. And of course, you can have, in order to talk about low energy supersymmetry, the Gravitino mass should be less than from here, of course, less than the supersymmetry breaking scale, and the supersymmetry breaking scale must be less than the species scale. On the other hand, this supersymmetry breaking mass is not necessarily they are not necessarily the mass splitting between the standard model partners, because it depends how what is the deviation to the standard model from the sector of supersymmetry breaking. In the case of gravity deviation, the soft terms are proportional to the Gravitino mass square, and therefore the soft terms are directly related to the Gravitino mass. While in the gauge deviation, the formula is given, and the Planck scale is replaced by the messenger mass times a U factor. And if the messenger mass is to the order of the supersymmetry breaking scale, then it's the other extreme limit in which the soft terms are proportional up to a U factor, the supersymmetry breaking scale. So it's take into account So the proposal is to combine this Gravitino mass conjecture with the dark dimension proposal and start with two possibilities. One possibility is that this scale, this complication scale related to the Gravitino mass, is the same with the scale of the dark dimension. So there is only one tensor tower that is associated with both hierarchy. Which is of course the most appealing possibility. The other possibility is that one has two towers, one associated to the dark energy, and the other associated to the supersymmetry breaking scale. Not to explain it to the not the time, the full hierarchy. We discussed the first possibility to have the same tower. In this case, by combining the two relations, one can obtain a relation between the cosmological constant, the value of the potential, and the Gravitino mass. Under this relation, where M is the exponent, the second. So this relation between the potential and the Gravitino mass can be identified actually as a leading power, non-balancing power, in the expansion of the superplace and to the decay, which implies that the n is integer or half integer, because 2n must be bigger than 1. Now, requiring that the supersymmetry breaking scale is less than the species scale, this implies that n is less than 2 or equal to 2, while imposing that the supersymmetry breaking scale is bigger than 10 dB, the Lipschitz constraint. On finding that then this order must be bigger or equal to 1. So there are two possibilities for any integer or half integer, v1, we have 2. The first possibility gives a Gravitino mass of the order of the planning stations of the gravity. And the supersymmetry breaking scale, which is of the order of 100 dB. 100 dB, sorry, which of course requires gauge deviation or type of gauge deviation to transmitted to the standard model sector. So that's an interesting case which provides further support to the next generation of colliding or medicine to continue searching for low energy supersymmetry. The other two possibilities give rise to a supersymmetry breaking scale, which is high, the order of the speed scale, and humanity, or just adjust, of course, to down. And Gravitino mass which spikes between the TV and the TV. The second scenario is which you have two calcified towers. In principle, it look more constrained. Sorry, opposite. That you have more freedom. However, it seems that finally there is also a lot of constraint. Which I explained here. So in this case, we have two towers, one associated with that dimension, the other associated with the supersymmetry break. The effective black mass on the speed scale is 5 plus p dimensional, where p as the dimension associated to the second multiplication scale. Then one has to impose experimental bounds that the second scale must be bigger than 10 MeV. There's a dimension comes from supernova. The supersymmetry breaking scale bigger than 10 MeV. And this leads us to two possibilities. Most of them are excluded. One possibility is this power, the second power, related to the supersymmetry breaking scale is 1/2. In which case, the supersymmetry breaking scale, which was the square root of the p, which was square root of the half, is directly related to the second scale, linearly. In which case, of course, it can be now anywhere, so it can be up to 10 dB before, and the speed scale varies accordingly. The other possibility is linear relation, again, for the second scale, in which case the supersymmetry breaking scale is high, and the Gravitino mass is worth 10 MeV. Now, what about possible string realizations? I mentioned five viable solutions. One in which the power between the Gravitino mass is linearly to the quantification scale, where can be R1 or R2, depending if it's 1 tower or 2 towers. The second possibility is the third. It's for the second scenario in which the supersymmetry breaking scale is and the other two cases in which the supersymmetry breaking scale should be ordered to the physics scale. All these three possibilities in principle can be realized by imposing short boundary conditions by the computation, where high dimensional fields remain periodic up to an anti-symmetry transformation that breaks supersymmetry, in which case the obtains the sequence the calcifying momenta by a parameter which is proportional to the alpha. And for instance, the Gravitino, in this case, the Gravitino 0 mode gets a mass which is Q over R, the Q is the ansatz. In the simplest case, takes for instance temperature gauging analogous to the temperature boundary conditions in which the fermions are periodic, and therefore the applicable frequency is not high. Of course, the most minimal, as I said, in the attractive scenario, the same tower. The vacuum energy is like one of the last before, and the Gravitino mass is lambda to the 1 over 8, same power. There is a realization of supersymmetry of this can be generalized. As I mentioned, the same words, the boundary conditions can be generalized in the presence of brains. And at least for deep brains, the result was that there is no three-level effect on the brain. So there is an open problem to obtain a consistent string construction, implementing the appropriate relation of function supergravity between the supersymmetry breaking scale and the Gravitino mass. The last one solutions in which the supersymmetry breaking scale are high, of course, are easiest to realize. By, for instance, the framework of plane supersymmetry breaking, in which you have only nonlinear supersymmetry breaking, the supersymmetry product at a string scale, and then, of course, the Gravitino gets a mass from the suppressed by the volume of the part, the light of the part. So, this plus. This phenomenon can be described also in the context of the effective supergravity, and in particular for multiplication, in which, by taking into account, for instance, the breaking of the non-scale structure by the loop correction or three-level correction depending on type relative and the constant superpotential obtained after stabilization modules. One obtains the right relation between the Gravitino mass that flows like 1 over r and the potential that flows 1 over r to the 4. Example, so the main conclusion is that the method that I would like to pass is that the smallness of some physical parameters in hierarchies that we have the faculty, there might be a signal that we live in the large distance from the singular scale of atom. And such parameters could be the scales of that energy which perceive the break. I mentioned that that dimension proposed for the cosmological constant can be extended, can be generalized by introducing relating to the perceived breaking. And two cases, and the most minimal cases with the same power, consequent power, is associated with both hierarchies, the supersymmetry breaking and the cosmological constant. But also the other possibility is there are two different towers, two different point of state, and the various possibilities, which in principle they can have string relations and described by supergravity.
Thank you very much for the nice talk. Are there questions, comments?
I think you mentioned earlier two possible shows for the source of dark matter, and they are The possibility that these two proposals are do elaborate.
It was more based on essentially the main point to explain is that in the case of citation, the mass of the dark matter will be decreased with the temperature, before lower temperature. So this requires that black holes increase their mass by increasing. So that's when we put in parameters and we lose in that.
One question. Yeah.
So the second scenario is the time of splitting of the six proteins and five close to the environment is same. Where the environment and so it's something isn't getting. I mean, in the first scenario, or in the later scenario, like the supersymmetry scale can be as high as 10 to 10 million, 29. It's not a coincidence that it makes the marketing for lateral synthesis and some the high possible scale for the specific brain scale is the species scale. If supersymmetry flow exists in some scale, you know, it's even if it is completely broken, broken means if it is realized in a nonlinear scale, it's a manifestation of lower cascade. Then this implies that at some level there is that level is the string scale. So it's not a natural.
Nice thought. Just one of my minor comments related to the neutrino mass we talked about. Stabilization in the neutrino level. The answer that people did recently was based on a very specific assumption about the bulk masses of neutrinos and all that. So the numbers and bounds that we wrote down with the function, it's easy to modify that to the bounds.
This bounds, yeah, the assumption that it's not only that paper, but since in the past that once you do the neutrino mass will be less than the quantification scale, so that the effect is the perturbation of the known analysis.
Right. I'm just saying that if you don't imagine the fermions in the ball, which are playing the role of sterile neutrino, their mass has gone much more parameter that they took. They just said it's zero. They took the bulk mass to be zero in their analysis.
The bulk mass they assume to be less than
Effectively zero in the sense that would change their parameter. Change that.
it will say. I'm not sure if this is viable. I mean, it's how it's.
Yeah, they have studied some papers studied the version where the mass were not zero, and they got about it's not reaching like 3 years minutes from now.
More questions? If not, then just make it.